So what I decided to do, instead of, we still got a little bit of extra time that I don't want to waste between now and break. So I was thinking today I want to concentrate mostly on just making sure everybody really has the test squared away. And then tomorrow we'll do a little bit more stuff with work and energy, some potential energy kinds of things. But today, mostly the test, also going over the homework. And tomorrow, if you have more questions about the test, I'd be happy to answer them. But that's the most pressing thing, so I'm getting that out of the way. Now, the warm-up relates to something that I always do in earth science. Got this 2-liter bottle, and I don't know if you've seen people make a cloud in a 2-liter bottle. If you were in my class, you can look out there and see who's there. Jackson. Remember when I made a 2-liter or a cloud in a 2-liter bottle? In earth science?
Yeah, I do.
Alright, so it's one of my favorite things to do. So I'm going to make this cloud, and I just realized one thing that's not so great is I've got a white table here. And in order to really see this, it works, oh my, look at my webcam. What the heck? I'm going to close my GoPro and see if I can open it back up, and maybe it'll be better this time. It was fine just a little while ago. Oh, come on. Try it again. I might have to disconnect it, reconnect it. Could use this other camera. Alright, now I can't get into the... There we go. That looks alright. I've just got to switch the view. So the first problem I was going to say is that I've got a white table, and clouds don't show up very well on a white table. Maybe I can use my computer as the backdrop, so you can see a cloud better in that. Alright, so the way that I'll make this is I've already got a little bit of water in there. I don't know if you can see the water sloshing around down here. Just need a little bit of water, otherwise there's nothing to make into a cloud. So I'll light a match and put a little bit of smoke in there. You can't really make a cloud unless there are some particles for the water to condense on. Get my match burning kind of well, and then I'll blow it out and stuff it in. Oops. Alright. There's a little bit of smoke hanging in the air. Now, gotta cap it up. And then at this point I just need to squeeze and release and squeeze and release. So what I'm gonna do is do some work on this bottle, on the air inside, and then the air is gonna do some work on me. It's like it's a spring. So I'll squeeze it, and then when I let go, it bounces back and pushes me. I'm pushing it, it's pushing me, I push it, it pushes me. So we're doing work on one another intermittently. So there, I'm doing some work on it. Now it does the work on me. And what I need is a bright light, but you can see, I think, that it's cloudy now. I'll squeeze, it clears up. Here, I'm going to turn the lights on. I don't know if that will allow us to see it any better. You can kind of see it. I don't know if how it looks on your end, but if you look in this area right here, cloudy now, gets clearer. Now it's cloudier. Now it's clearer. And unfortunately, I just don't have a really bright light source to show the cloud itself. Anyway, one of the best things to do. I don't think I'll have bright enough light here, but usually when I'm done, I can make smoke rings, and no, you can't see those. In a classroom, I do this over the overhead projector. So the question is, can you explain what happens here in terms of work and energy? And this is kind of a chemistry question and a physics question, and I guess an earth science question all together. So I'll lead you through it, and you don't have to answer out loud. You can if you want to. So when you see a cloud form, which phase of matter are you definitely not seeing? Solid, liquid, or gas? Which one of those is invisible? And the answer is gas. So when the cloud forms, when it gets cloudy in here, it's not a gas. It's either a liquid or a solid. And since it's not below freezing in this room that I'm in, we can rule out solid. So what's happening is I'm making the phase change back and forth from a gas to a liquid, from gas to a liquid. So from chemistry, you should have an understanding of kinetic molecular theory, the idea that when you heat up molecules, they move faster, and when you cool them down, they move slower. And if you heat them up enough, they can change phase from, say, a solid to a liquid. Heat up the liquid even more, it can turn from a liquid to a gas, and then when you cool them down, they go the other direction. So when I was squeezing this, and it was becoming clear, that meant it was turning, that water inside there was turning to a gas, because it was becoming invisible. When I was letting go, that water was turning back to a liquid, and that's why we could see it. And you couldn't see it very well, but I could see it pretty well. So when I squeeze, it's clear, the water's turning to a gas. When I release, it gets cloudy, the water turns to a liquid. So in terms of work and energy, can anybody explain why that was happening? Why was my squeezing causing this to turn to a gas, and then my releasing causing it to turn back to a liquid? Can anybody explain that? And you can butt in at any time, but I'm going to show you my notes and highlight what I think is the important part right here. This is the work energy theorem, that net amount of work is equal to the change in kinetic energy. But above that I have work can be thought of as equivalent to energy. When work is done on an object, the object gains energy. When work is done by an object, the object loses energy. So think about this. When did I do work on the object? Was that when I was squeezing it or releasing it? And the answer is squeezing it. So squeezing it. I did work on it when I squeezed it like this, and then it did work on me when I released. It pushed back. So I push it in, and then it pushes back. So when I do work on it, it's gaining energy. On a molecular scale, what I'm doing is all those little particles that are bouncing around in there in whatever gas form, gas form. When I squeeze, I give them a push and they go faster, so that heats up the inside of the container. And then when I release, they push me back, so they do work on me and they lose energy. So I'm putting energy in when I squeeze, heating it up, and then allowing it to push back against me and lose energy, cooling it off. This is not a great illustration in the sense that in this unit we're really concentrating mostly on mechanical energy, and what I'm talking about in this is thermal energy. On a really small scale, the particles in here, the molecules, atoms, are bouncing around, but they're kind of in random motion. So if I heat up the inside of this bottle, it's not like the whole thing is going to start moving one way or another. It's just that those random motions inside are going to speed up, and that's thermal energy. But anyway, the whole point of this warm-up is to just show I'm doing work on something, giving it energy, and then I let it do work on me, and then I take its energy back. And you can see that in the apparent heating up, making the cloud disappear, and the cooling, which is what causes the water in the cloud to condense. And as usual, if you've got any questions, you just blurt them out. But nobody ever seems to have too many questions about things like that. The homework. I want to go over the answers to the homework and give people a chance to ask questions, keeping in mind that this is not the most important thing right now, because we've got time to work on this before our test, which is going to be sometime after break. But go over what the answers were. So I've got the answers are written here, but I can go to my solutions and give you more complete answers if you want.
Can you show 5D, please?
Sure, 5D. So 5D was, so 5D and F, I don't know why there's no 5E, but 5D and F are kind of the same thing. They're both about the car slowing to a stop using the brakes. And the only difference between D and F is D happens with the, let's see, D happens with the higher coefficient of friction, because that's static friction, there's no skidding, and F happens when somebody presses the brakes too hard and they lock up and then they slide. So let me go to the solution.
I didn't know when you would use the static versus the kinetic.
Was that
the kinetic?
Yeah. So if the car's riding along and the brakes are locked, somebody hits the brakes really hard and the tires stop turning entirely, and the wheel rubs against the road like this, then that would be kinetic friction. Anytime two surfaces are scraping past one another, that's kinetic. When you don't lock the brakes, the tires never really skid, so they just roll slowly to a stop, and there's never any motion between these two surfaces. So does that answer your whole question, or?
Yes.
Okay. So other things. We've still got, there are a lot of other parts to these. Does anybody have any questions about any other?
Can you do 2B, please?
Yeah. All right. Yeah. Somebody asked me about this one, and I was going through this, and I kept getting, well, I got my answer, and then I was getting some crazy answer, and so it is kind of confusing. There are multiple ways to do this. First, I'll say that. And I think I'm just going to go forward to wherever I had my work before and talk about what I did, but maybe I'll just do it. I'll do it right here. Here's the sled. It doesn't really look very much like a sled, but somebody's pulling the sled and applying a force of 100 newtons, which really isn't important right now for what we're doing. But that force is applied for 1 mile, so this distance is 1 mile. And if you do that, and you calculate the work equals force times distance, you end up with 161,000 joules, or 161,040 joules. So that's how much work is done. And B is really just about finding how many Snickers bars give us a number of calories that would be equivalent to that much energy. So calories are just a different unit of energy than joules. So the way I did it is I took the number of calories in 1 Snicker bar, and I took this efficiency of the dad's body. So this 30% means he might be eating 260,000 calories, but he really can only do this work with 30% of those. So that was the first thing I did. I just did 0.3 times 260,000. And I got the number of useful calories in a bar. And this isn't the way you would have to do it, but it just seemed like a good way for me to do it. 260,000 times 0.3, 78,000. But now I've got joules, so I should write calories per bar. So 1 bar is really equivalent to 78,000 calories. And 1 calorie is, I've got to look it up here, 4.184 joules. 1 calorie is 4.184 joules. So I need to get this converted into joules so that I can see how many of these this is equivalent to. So 78,000 calories. I guess I could write calories over bars, but yeah, I'll write calories per bar. And I want to get rid of calories. I want to have joules instead. So these two are equivalent, which means I can multiply this by this over that, or that over that, and I'm still multiplying by 1, so it's all good. But if I want calories to cancel out, I need 4.184 joules per calorie. So this is going to give me the number of joules per bar. 78,000 times 4.184 equals 326,352 joules per bar. And so let me write this a little bit differently. I'll just say 326,352 joules equals 1 bar. So I've got this many joules. I want to basically now convert that to bars. And here's my relationship. So these two are equivalent. So I could either multiply this by this over that or that over this. But I want joules to cancel out, and I want to get bars in return. So I'm going to take the 161,040 joules and then multiply this by 1 bar over 326,352 joules. One thing I like to do, I don't know if you use this shortcut too, but since I already have this on the calculator, I can either divide this number by that, but I've got that on my calculator now. So the other thing I can do is I can multiply this by 1 over that. So I can just take the reciprocal using the 1 over x and multiply that by 161,040. So it's 0.49 bars. And if you don't like that method, 161,040 divided by 326,252. Oh. Oh, I hit clear twice. Dang. Having trouble. 161,040 divided by. There. Alright. So, if you did it a different way, and you don't know why your way didn't work, I don't know if this is still satisfying or not. So, how's that? Does anybody need more explanation or want me to do it a different way, or what do you think? I'm taking that as an all good. Either that or you're all frozen. Can't tell. Just talking in circles.
We're not frozen, I don't think.
Thank you, Adolin. All right. So are there any others? Any other of these questions that I can go over and illuminate for you? All right. Moving on then. So here's what the test is going to be like. We've got about 24 minutes before 10:45, and you really already kind of know this because I've told you that I gave you that last practice test that I gave you was last year's test, and I had two versions of that, and they both followed this format. I haven't gone back and checked, but I'm pretty sure they follow this format. So they're going to be 10 to 15 multiple choice questions, covering centripetal motion, law of gravitation, and then all three of Kepler's laws. You need to know, even though we haven't really focused on the first law, you need to know that the first of Kepler's laws is that all orbits are elliptical, and the object being orbited is at one of the foci, like at the focus of the ellipse. But that's really an easy one. That would just be in a multiple choice question of the variety that would say, which of the following is not a Kepler's law? And if you see all orbits are elliptical, that is Kepler's law. And then the other two are the law of areas, sweeping out equal areas in equal times, and then the third law with periods and orbital radii. So 10 to 15 multiple choice over that. Expect some multiple choice where your task really is to analyze a formula, probably one of these kinds of formulas, and you might have the question, suppose you have a certain force of gravity. What's going to happen to the force of gravity if the radius quadruples, the distance between the two masses quadruples? What will happen to your force of gravity? And you'd have to think about this formula, think about what would happen if you multiply r by 4, what would happen to that force, that kind of thing. There's definitely going to be something like that. And, sorry, I'm waiting to get back to the page. Problems, 3 uniform circle problems. So, see the chart on the right for possibilities. We can go through some examples here in a little while, but I was trying last year to think through different types of problems. So you could have a horizontal circle, and that would be like a friction could be the cause of the horizontal motion. If you have a car that's just driving around a track in a circle on level ground, going around in circles, friction would be providing the force keeping it in the circle. You could have a ball that's going around, that's being swung around in horizontal circles on a string, and string tension is holding it in. Or this could be like the Spaceship 2000, whatever that thing is at the fair, where you go around in horizontal circles and you're thrown outward against the seat. So those are some horizontal scenarios. Then vertical circles, that'd be, instead of being like this is a horizontal circle. Vertical circles would be like this, and that could be caused by a string. You could have something that's held in by a string. You could also have something that's like another ride at the fair where there's a normal force pushing you in. This could also be a Ferris wheel kind of thing where somebody's standing on this and going around in a circle. So there are a lot of different ways these could work. We could have circles in space where there's a string and something going around orbiting a ball on a string in space. You could have a planet orbiting the sun and gravity is holding it in its circular motion. You could also have normal force, and this would be like the artificial gravity of a space station where there's this hamster wheel out in space going around, and people who are out on the outside of it experience simulated gravity because the normal force of the floor is pushing on them. And these conditions, I want to come back to this in a little while and quiz you about these. These are kind of interesting, but I don't want to say anything yet. So there are going to be 3 problems like that. And there are 3 boxes here. I don't really remember if that meant that there's a horizontal circle problem and a vertical circle problem and a circle in space problem. Not really sure. Circles in space, though, that sort of spills over into law of gravitation problems, Kepler's third law, And then, so a lot of these are things in space. There's going to be definitely one where you're going to have to kind of directly apply Kepler's third law. There's going to be a direct application of the law of gravitation. Something relating to the formula for the velocity of a satellite in a circular orbit. So go into the formula here, well, and then something related to the formula for G. So the formulas I'm talking about here are this one, G equals big G times the mass of the orbited object, or sorry, yeah, the mass of the orbited object or the planet that's causing the gravitational acceleration and radius. So there's going to be some kind of a problem where you'll have to use that. You could be solving for any of these things. I could give you the acceleration of gravity. I could say you're near some planet, you're dropped, you begin to fall at a rate of you're accelerating toward it at 4 meters per second squared, and you're so far from the center, what's the mass of the planet? Or maybe I give you the mass of the planet and you have to figure out how far away you are. Or maybe you're given the mass and you're given your distance from the center and you've got to figure out G.
I have a quick question.
Sure, Oliver. Ollie. Sorry, Ollie.
For when like something's falling down to Earth or something's being pulled in down to Earth, use the mg equals the force of gravity.
Mm-hmm.
And then when something's like orbiting a planet, use the mv squared over r equals force of gravity.
Yeah. Well, let me draw a picture and talk about that. So
I mean, I'm confused because if everything's an ellipse, the radius isn't always going to be like the same.
Right. So let's just say, and may take me a while to really answer your question. I just want to clarify what. So you were saying mv squared.
If you're trying to find the velocity of like a satellite orbiting the Earth, you would use that.
Yeah. So here are the things that I think of when I say that, when I'm thinking about this. So if this is the center of the Earth, this is the center of the satellite, here are some things you could do. You could find the weight of this satellite. This one I'm going to put a little asterisk next to. The weight equals the force of gravity equals mg. Now g up here is not going to be equal to 9.8 meters per second squared. So if you had the satellite sitting on the ground, if it were sitting right here, if this were the satellite, then you could say the weight would equal mg, would equal the force of gravity, and this would be the mass times 9.8 meters per second squared. So on the ground right here, g equals 9.8. But as you get farther out here, g is going to be less and less and less. So g, if you wanted to calculate it at different points away from the Earth's surface, then you would use the formula g times the mass of the planet over r squared. So if I use that formula, if I use 6.67 times 10 to the negative 11th times the mass of the Earth divided by this radius right here squared, I'm going to get 9.8. But if I do it and I use this radius squared, then I'm going to have a bigger number in the denominator, and g is going to be smaller. So technically you can say mg works here, and mg works here, and mg would work way out here too. It's just that value of little g is going to change because the radii are changing. And always that would be the weight, really. So if you were tall enough to stand here, stick way out, need you to hold it. So if you were tall enough to stand up here and hold this satellite just still out in space, you'd have to apply it. You would feel the weight of that satellite, and it would feel a lot lighter than somebody who's holding the same satellite down here. because the gravitational force is weaker when it's farther from the Earth. So so the mg does work. You just got to be careful that the value of g, which is 9.8 at the Earth's surface, is going to be different at different heights. And what you could also do, instead of using mg, the more direct way to do it would just be to say the force of gravity equals big G times the mass of the Earth times the mass of the satellite over r squared. So that just gets around even having to bother with, all right, what is the acceleration of gravity when you're out here or out there? You can directly use that. Now, if these things are in motion, if this is in motion, if we assume that it's in circular motion around the Earth, let's forget about it being in some weird ellipse. If these are really orbiting the Earth, then you can say that the net force is mv squared over r, because they're in circular motion, and net force is always mv squared over r in circular motion. And the only force acting on these when they're in circular motion is the force of gravity. That's the only force that's at play. So we can say that the force of gravity equals mv squared over r. And that's where some of these formulas come from. Because this is in a uniform circle, always, always, always the net force is mv squared over r. But since that force is the force of gravity, then I can set it equal to this, and I can say it's g mm over r squared, and then I can solve for stuff here. I can simplify this. I can divide both sides by the mass of the satellite, and then multiply both sides by r, and then take the square root of both sides, and that's where I get this formula, which allows me to calculate the velocity of any of these satellites going around. Their velocities are going to have to be faster when they're closer to the Earth. If you shrink this r down, shrinking the r in the denominator there, that's going to make this velocity faster and faster, which kind of makes sense. If you think about how fast something would have to go around here to overcome that really strong gravitational pull, it's going to be faster than if it were out there. All right, Ollie, I said that wasn't a simple answer, but do you have any questions remaining? Because if you do, I can hit them.
That clears things up a little bit.
Yeah, it sort of clears them up and sort of complicates it, but it's a complicated thing. And we can talk, so go back and try some, whatever it was that tipped you off to the fact that was confusing, go back and try some of that tonight, and then we can, if you have more questions, more specific questions tomorrow, we can talk about it again.
Alright.
So let me go back to where I was. And anybody can insert your questions at any moment. So yeah, I think we got off there where I was saying there's going to be something relating to that velocity formula, basically the one that I just derived, and then there's going to be something relating to the formula for little g, which is the acceleration of gravity. And I updated this list. I used to have some, in past years, we ran across one of Mr. Pennington's formulas where what he does is he takes this v equals the square root of gm over r, and he substitutes square root of gm over r for v down here, and he comes up with another formula for period. But you don't really need that. If you can do this and you can do that, you don't need to make yourself a whole new formula. So on the test, you'll get all this stuff. This will all be, this will be on the test itself. Nobody can reject that. You can cover your eyes and not look at it, I guess. But these other ones, these will be on the little formula sheet that I'll give you. But these are the other ones that you either need to be able to derive or know. So, and this, this is rate equals distance over time. This is weight equals mg. Those are useful for coming up with some of these other formulas here. So, questions in general about anything I've said so far? All right, let's, since we've got this so-called 4-minute drill, I've got about 4 minutes. Let's see how you can do on this. So the 4-minute drill is, I'm sorry this isn't numbered, and it's really annoying that my screen is, I guess that's the whole thing. Hopefully you can see that. So, Mr. Pennington would give people 4 minutes to do this. I'll give you about 4 minutes, and then we'll go over the answers. Maybe I'll give you a little bit longer. So see if you can write down either the formulas or basically whatever this is asking for. The first one, centripetal force in terms of R and V. Basically, what's the formula for centripetal force in terms of R and V? See how you can do on this. In about 4 minutes, I'll go over all the answers. It's totally okay if you don't understand what he's asking for. Hopefully you've got some scrap paper somewhere. Just realized I had this on a sheet of paper. Maybe that's not as good. I'll switch to it in a minute. I honestly don't remember when I started the so-called 4-minute drill, so I'm just going to go until 10:42 and then reveal the answers. instead of writing them down, I'm just going to click on my solutions here. So here we go. Centripetal force in terms of R and V is, and I guess it's also in terms of M, that's just mv squared over R. That's the net force anytime something's in a circle. Centripetal acceleration is v squared over R. So you put them together, or you put the acceleration together with force equals ma, and you get mv squared over R. The tension in a string keeping a mass moving in horizontal circles of radius r is mv squared over R. So if you only have one force really that's acting on something, then that force is the net force. So if it's a string, then the string is providing the net force. Now it gets a little more complicated. The tension in a string keeping a mass moving in a vertical circle, at the top of the circle, the tension is mv squared over R minus mg, and at the bottom, it's mv squared over R plus mg. And I should probably give you a quick explanation for that. So here's the object. And the net force at the top is negative mv squared over R because the acceleration is downward. And the only force acting here is, well, there are two forces. There's the weight of it, and there's also tension. So those are both negative. So I can say the net force is negative mv squared over R, and I can also say it's negative t minus mg. So to solve for t here, I'm just going to add t to both sides, and I'm going to add mv squared over R to both sides. So basically I've taken this over to the right side, taken that to the left side, and I get that. So the tension is going to be a little bit less than mv squared over R up at the top. Down at the bottom, the tension is upward, the weight is downward, and the net force is positive mv squared over R because it's, again, it's toward the center. So I get mv squared over R is the net force, and that equals positive t minus mg. And to solve for this, I'll just add this to both sides. I get mv squared over R plus mg equals t. So if you swing something around, the tension is going to feel a lot stronger in the string at the bottom. It's going to be mv squared over R plus the weight, but at the top it's going to feel less tight because you're going to be subtracting the weight. Ooh, time's up. Let me quickly go through the rest. So gravitational force between two bodies, that's just Newton's law of gravitation. The acceleration of gravity, that's the calculation of little g, m over r squared. And then finally, the velocity of an object in circular motion around a planet is square root of gm over r. Oh, I guess that's not the last one. Last one's Kepler's law, with the t's squared and the r's cubed. So that's it. If you have other questions about the test, we'll talk about them tomorrow. We're just going to go over the potential energy if we have time, but if people want to ask more test questions and that takes up all of tomorrow, that's fine with me. Feel free to go or stay